All right, today we're going to take a little look at physics, forces, and free body diagrams. So in physics, we use a certain tool called free body diagrams. And all that really is, it's like a picture labeling the forces that are acting on an object. And remember, forces are vectors, which means they have a magnitude. So a bigger force will be longer in length for the arrow. And they also have a direction. So if you're going north, then the arrow will be aimed north. If you're going east, it'll be aimed to the right or east. Just remember, forces are vectors, so they have a magnitude, which is just a number, and they have a direction. And that number we show by how long the arrow is representing the force vector. And it'll make more sense once we do it. So directions. For the following questions, please use the steps for success and draw large free body diagrams with clearly labeled forces. So this is a big step in physics. I'm going to say favorite animal. I'm going to say dog. Big dog fan. Put an exclamation point. So there are 5 steps for success. You draw a picture, you label your forces, you show the coordinate system, you sum your forces, and you solve. And actually, I might edit this worksheet and put the number 5 right there, because if you follow those 5 steps, you'll have a really good chance of getting them right. And we're going to have some different forces we use in this worksheet. We have the force of gravity, also known as your weight, and the symbol you use for that is Fg, or W for weight. I tend to use Fg, force gravity. My twin bro, Mr. Laurent, he uses W for weight. It's the same difference. I just use Fg for the force of gravity. Normal force. And the normal force, like when you push on a table, you put a force on the table, and the force that gets pushed back on your hand from the table onto your hand, that's the normal force. It's like the pushback force. It's a result of Newton's third law. For every action, there's an equal and opposite reaction. So we'll talk more about the normal force, but if you want to think about it like when you make physical contact with like a table, or you're touching a wall or a door or whatever, the normal force is that's the feeling you feel of the door pushing back on you or the table pushing back on you. And the force of friction, if we're going to the right, like we're dragging a sled to the right, the force of friction is going to be fighting it to the left. So friction opposes motion, which just means it goes in the opposite direction of the motion. And the symbol for force friction is just FF. Normal force is Fn, and force gravity is Fg. And then if you ever have a rope or like something like that, like you'd have tension in your bicep muscle, or like strands of fibers or whatever. So the force of tension is used for a rope or anything that can have like a force throughout it, like a muscle and things like that. We have the force of air resistance. We just call it Fr. And if this is a lot, I'm just kind of going through them. And once we use them, they'll make more sense. So other things to think about. Sometimes they might say something like you have the force of a kick, like somebody's kicking something. Really, that's just the normal force. But if you want to call it Fk for force kick, or if you're pushing something, Fp for force push, as long as I know what you're doing and it kind of makes sense, you'll be okay. All right, so let's do some examples here. I have some hints. Force gravity is Fg. It's the same as weight. And force gravity is whatever mass you're talking about times the gravity. Remember, little g is 10 meters per second squared, or 9.81. We'll call it 10 meters per second squared, and it is downward. Let's just do some examples. Number 1, a block is sitting on a table in equilibrium. So it's not moving, it's just sitting and hanging out on a table. So we're going to draw a table, and we'll draw a block. Here's our block. It's just sitting on the table. Now I look back at my steps. I say step number 1, draw a picture. Did it. Step 2, we're going to label the forces. So the forces acting on a block, you have to ask yourself, well, if I'm on planet Earth, well, automatically from the center of gravity of that object, we're going to have the force of gravity acting Fg, pulling straight down. And if you only had one force on the object, that object would not be in equilibrium because that object would be moving downward. But you have to ask yourself, what's preventing the object from moving downward in this case? The block feels the table. And remember, for every action, there's an equal and opposite reaction. So this block's pushing down on the table is pushing back up on the block. And that force, that pushback force from the contact, that's called the normal force, Fn. And the reason they call it the normal force is because the table is flat like that, and the normal force is going straight up, and the blue table there and the pink vector arrow, that makes a 90-degree angle. The word normal means 90 degrees. Don't worry about that, but the normal force is always going to be perpendicular to the surface. So step 1, we drew a picture. Step 2, we labeled our forces. And we have to ask ourselves, are there any other forces acting on this? There's nothing pulling it to the right or left. We just have 2 forces. Gravity's pulling down. The normal force, for every action, there's an equal and opposite reaction, is pushing up. So the forces come in pairs, just like Sir Isaac Newton said they would. For every action, equal and opposite reaction. So there's no other forces. So then we can say, okay, we did step 1, picture. We did our forces. Now we have to show our coordinate system. And you might be thinking, like, what do you mean by show our coordinate system? Because in math class, you always just say, hey, our y is going up and our x is going to the right. Just the standard coordinate system. So it's kind of like in math class, the x is positive to the right and the y is positive up. So you're like, okay, that's just the normal coordinate system. And what you're doing is you're saying that the normal force, see that pink arrow is going up? That's the positive y direction, since that lines up with this right here. You can hear Penny, my dog. She's scratching her ears. And then force gravity is pulling down. That'll be a negative force. The coordinate axis there just tells you which way you're defining positive and negative. Up will be positive. Down will be negative. Right will be positive. Left will be negative. If that doesn't make sense yet, once you do a couple, it'll make sense. So, all right, picture. Labeled our forces. We showed our coordinate system. And step 4, we're going to sum up. We're just going to add up the forces in each direction. When they say the word sum, that just means add them up. And in math class, maybe you've seen this symbol before. It's the Greek letter sigma, which just means add it up. So you're going to add up your forces in the y direction. If you don't like making Greek letter sigmas, all that symbol means is add your forces. Add your forces in the y direction. So in the y direction, we have the normal force. And that normal force, since it's going upward, and we said upward is positive, it'll be a positive force. I'll put a plus there just to tell you I thought about it. And so we have upward force there with the pink normal force. And then we have one other force, gravity's pulling down. So we'll say minus force gravity. And so we added up our forces. That's what we just did right here. And we always set our forces equal to MA. But here's one thing they said, a really key word. Remember Newton said F equals MA, but they said a really important phrase. They said this whole thing's in equilibrium, which means it's not moving. The net force is equal to 0 newtons. So there's nothing happening in the y direction. You have Fn going up, you have Fg going down. Those two forces cancel, and it's just not moving. It's just sitting on a table. If you want to do the x direction here, we'll do the x direction. I'll go purple. So we sum our forces in the x direction. Let's look at our diagram. This is our FBD, free body diagram. If you want to think about it like a physics picture, that's all it is. You just drew. There's nothing going on in the x direction. We got nothing going left or right, so we just put 0 newtons. So that's kind of a simple one. Step 1, we drew our picture. Step 2, we labeled our forces. Step 3, we showed our coordinate system, how we're defining positive. In our case, we said positive is up or positive is to the right for the x direction. We summed up our forces, just add them up. But here's the deal. We didn't solve for anything in question 1 because they didn't really tell us much. We didn't have anything to solve for. So we'll do more of that later once they actually tell us a little more. On a question like this, I had to give you a point for sure for drawing a good FBD, a point for your equation, a point right here, and a point for your answer, which we don't really have an answer on a question like this, but you get like 4 out of 4. Okay, so make sure you show your work. And then let's do question 2. A block is sitting on a table. It's not moving, but there is a rope pulling straight to the right and friction preventing it from moving going to the left. Do steps 1 through 4. So it's the same thing. We're just going to set up with just that we have some X stuff happening now. So I'll draw a good picture. All right, so there's our block. And then we're going to start labeling our forces. And it's literally, you read the words and you put the forces in there. As soon as you're on planet Earth, you know the force of gravity is going to be pulling you straight down. So Fg, the weight of the block, is pulling straight down. And you know forces can never come by themselves. So you say, hey, you know what? For every action, equal and opposite reaction, the block's pushed on the table. The table's pushing back on the block, Fn. And so we have those two forces. And you're thinking, whoa, whoa, whoa. This is the same as last question, but it's not because there's a rope pulling to the right. So there's some rope pulling to the right. Now, if you forgot how to label the rope, look back here. You're like, oh, the force of tension often used for rope. So ropes, we just say, oh, that's force tension. There's tension in rope. We'll call it Ft. Just like that. And it says, and to the left, there is friction. So Ft, the rope wants to pull it to the right. The force of friction, Ff, is pulling. I tried to make that horizontal. That's not a very good horizontal gray line. But so the tension wants to pull it to the right, the orange vector. But the force of friction says, nope, not going to let you go there. So those two vectors are equal in magnitude, but they're opposite in direction. So step 1, we drew our picture. Check. Drew our picture. Step 2, we label our forces. Step 3, we're just going to show our coordinate system on there again, just like we just did. And it's kind of boring because the ones we do for now are just going to be a standard XY coordinate system, just like you'd see in math class. Positive is to the right and positive is up. We're just telling the grader, like, hey, we're calling to the right positive and up positive. Kind of makes common sense. And then if we're looking at our steps to success, and I'll say there are actually 5 steps for success, but we're not going to get to number 5 yet. We're going to add up our forces in each direction. So let's start with the y direction. So sum our forces in the y equals, and in the y direction, see the y is going up and down. We say any force that's up or down, so we say positive Fn minus the force of gravity. And we say it's in equilibrium, it's not moving, so we'll say, hey, you know what? We're going to set that equal to 0 newtons. And then in the x direction, last time we had nothing going on left and right. This time we have 2 forces. We have force tensions pulling to the right, and see how positive is to the right. So Ft will be positive. That's that force pulling to the right minus the force of friction. And that, since it's not moving, is equal to 0 newtons. So if it's not moving, it's kind of boring because it's kind of like saying I put $10 in my bank account and then I took $10 away, the net balance is 0. That's actually what they're saying by equilibrium. It's saying, hey, you put some force in, And there's some force trying to stop it from moving, so the net force is 0. So yeah, that's just kind of setting it up. So there's question 1 and question 2. Let's do a little bit tougher one. This is going to make us solve and get a number answer. And this might be the last one we do for today. A block is sitting on a table. On the right of the block, there is a rope attached and a person pulling straight to the right with 10 newtons of force. So they're giving us numbers, so we're actually able to solve this one. The force of friction opposes, so it's going to be, the force of friction is going to oppose it, which means it's going to be going to the left. If you picture it's like a tug of war, somebody's pulling with 10 to the right and friction's fighting with 5 to the left. You can picture that the overall block is going to move to the right. Let's just draw this down and always draw our picture. Boom. Our block right here. And sometimes they give us the mass. I'll actually just straight up put the mass in the block. So the block has a mass of 5 kgs, just so I remind myself that. And then as soon as you know you're on planet Earth, draw the force of gravity, because remember, force of gravity is pulling straight down from the center of mass. And then the block's touching the table, which means the table's touching the block and pushing back on it. So we'll put the normal force pushing up on it again. So you can kind of see a pattern that forces always come in pairs. And then here's the really important thing. Let's say in this case, you're pulling the right with 10 newtons of force. So the force tension is pulling the right. And they're actually straight up telling you that's equal to 10 newtons. They're saying, hey, that has a number this time. It's not just a letter. And they're saying, but the force of friction opposes the motion, which opposes just means it's going the opposite direction. And one little thing, the orange vector is 10 newtons. The gray vector is 5 newtons. So technically the orange vector should be twice as long as the gray vector. I'm not going to get a ruler out and measure that, but just make sure since that one's bigger, it should be longer because that's how we show that it's a stronger force. Okay, so and then we say, okay, force of friction is 5 newtons. And I didn't put the negative in there because I'm going to put that in later, but I showed that it's going to the left just like that, which is a negative force. So we say, all right, step 1, we drew a picture. Step 2, we label our forces. Step 3, we're going to show our coordinate system. And you're like, what? We just keep showing the same thing? Yeah, we just show them how it's done. X, Y. So the right is positive, the left is negative, up is positive, down is negative. And if you ever take more advanced physics course, like in college or something like that, you're going to start doing really fancy things where you can tilt your coordinate system. So I'm just trying to get us in good habits of putting it right there. So we did our first 3 steps, and then step 4, we're going to sum our forces in the Y direction, and sum our forces in the X direction. Now, very important, they say do steps 1 through 4, then finish by doing step 5 to solve for the net acceleration in the X direction. So this is the one I'll put a star here where we're actually going to get a number, star. I don't know, I made kind of a weird star thing there, but all right. So let's just take a look at the Y direction. We have normal force going up. And so Y direction, if you want to think up and down, minus force gravity. And picture this, the block isn't rising or falling. Nothing's happening up or down. What's happening is there's a tug of war left and right, and it's going to move left and right. So if nothing's happening up and down, the net force in that direction is going to be 0. So this isn't super helpful. We can write it, but it's not going to help us get the acceleration in the X direction. If we want to find the acceleration in the X direction, that's when we're going to do this step right here, and we're going to sum our forces in the X direction. So we'll say tension is positive because it's going to the right, minus the force of friction. Now, here's the deal. They said solve for the net acceleration, so we know this thing's going to be moving. They're saying it has an acceleration. And remember, before we had said equal to 0 because they just weren't moving. But in general, Newton said F equals m times a. So if it's going to be moving, you have to set your individual forces equal to ma. That's Newton's second law. And if that's kind of a tough step, just tell yourself, well, they told me there's going to be an acceleration, and we just have to find it. Now, here's the deal. They told you the tension was 10 newtons. So I'm going to plug that in for my tension. Minus the force of friction is 5 newtons equals m times a. Well, the m of the block is right there. It's 5 kgs. Just like that, times a. And if you don't like the labels on there, I'll just make it look a little bit. 10 minus 5 equals 5a is your expression, your math expression. So you're like, oh, okay, 10 minus 5 is 5 equals 5a. And you're timesing 5 by a, so solve for a divided by 5 on both sides. The acceleration of this block is 1 meter per second squared. And here's the deal. That number is positive. So that means the block is going to the right, because you said anything going to the right is positive. So positive 1 meter per second squared. That's the net acceleration. It's like there's a tug of war between tension and friction, and the net acceleration is going to be to the right 1 meter per second squared. Okay, so I'm going to go through, I'm going to finish up making my key for the last ones here, but I'm not going to record the video, so that'll be a good place to stop. But if you want to go back and check the key, go ahead and check the key. This will be where the video stops, but hopefully it gets you started, and then the last questions here you can do on your own. So thanks for watching.